Okay, so just to give you guys an idea of some of the stuff I had for you. So you have the Hess's law, the notes. Um, that obviously I put that in there. We'll get to that in a second. Um, Two of the other sheets I gave you, these are um, these are sample exercises from the book, but instead of you guys having to kind of copy all of it down, I just made copies of the little Rocketbook page things, blank copies, to give to you, and then like we'll do the work out on these. But and obviously I will post these. I'll post the completed versions of these to Google Classroom as well. But I thought it'd just be easier if you had a blank copy to fill out as we go along, so you don't have to like rewrite all the problem stuff and everything. Um, okay, so and then the last thing you should have is a copy of the homework. The where did I throw that? It should just say, yeah, Hess's Law, worksheet 5-6, this thing. Right? Okay. So everybody's good on those? All right. Here we go. So Hess's Law. Hess's Law is actually relatively simple in a concept. Hess's Law just says, if a reaction is carried out in a series of steps, the delta H, the change in enthalpy for the reaction, is the sum of the change in enthalpy for each of the steps. The total change in enthalpy is independent of the number of steps. So what it kind of means is it doesn't matter if it happens in one step or 5 steps, the total change in enthalpy overall will be the same. Okay. Which makes sense if you think about it, because if you had like, so say you've got something with a beginning enthalpy and an ending enthalpy, right? And say you went up, I don't know, say you went up 50 kilojoules from the beginning to the end, from your reactants to your products, right? You go up 50 kilojoules. Now, does it really matter if you technically went up 25, then down 100, then, up 125? Like, no, it doesn't really matter, like, in between how you did it. If you gain, like, how much you gain, like, all that really matters if you're just comparing the beginning and the end is the difference between them, right? So that's kind of what they're saying here. It says it doesn't depend on the number of steps or even how those steps go, really, other than to say your total beginning energy and your total ending energy are what you look at to find the change in enthalpy overall. Okay, so that's what this next part is saying too here. The total delta H is also independent of the nature of the path. All right, so what we have here is we've got two equations. Okay, so we've got reactants and products. We've got methane, CH4, and oxygen gas reacting to form carbon dioxide and water. So what kind of reaction is that? The top one. Yeah, good, combustion, right? You got a hydrocarbon and oxygen making carbon dioxide and water. Good. Now, that equation, the way it's done there, kicks off 802 kilojoules of energy. In other words, from the reactants to the products, it loses 802 kilojoules, gives off. Right? So what kind of reaction is that? Exothermic or endothermic? Exo, good. Giving off, right? Losing energy, giving it off is exo. All right. Then if we look at the second equation here, this one is kind of weird because it's not really a chemical equation. It's not a reaction, I should say. It is an equation. It's not a reaction. What's happening here? Yeah. Yeah, good. Losing energy, and we're getting a state change, right? We're getting water turning from a gas to a liquid. So it's not actually a chemical reaction. It's a change, but it's not really a reaction. But we do it in the equation because we do have a change in energy. So what happens is the water as a gas gives off another 88 kilojoules, and it turns from a gas to a liquid. So this, if you notice, from here, in the first one, it gives a gas, right? And then in the second one, that gas turns to a liquid. So if we look down here, what they've done in this bottom is they've sort of almost added them up. They've combined the two equations. And what you have is the beginning reactants, and you have the overall final product after both of these occur. Okay? Because the first one, when it occurred, you got CO2 gas and H2O gas. But then that H2O gas turned into this. So essentially what you're doing is you're substituting this product in here for this. Does that make sense? Okay. If you have questions or you don't understand where something's going, let me know, because there's yes, there's some math, there's some stuff we can do, but a lot of this is just sort of, it helps if you understand the concept. So if something isn't making sense, please stop me. Okay. All right. So, and then you can see, look what happens to the delta H's. They literally just combined them and added them, right? Negative 802 plus negative 88 gives you a negative 890 total. Okay. All right. So that's this here showing it's combined. Then it says, note that delta H enthalpy is sensitive to the states of the reactants and the products. So the states of the reactants and products, what we were just talking about, right? The gas, liquid, that kind of stuff that cause it to gain or lose energy, it matters. Then also, another something that I put an asterisk and this is really the only thing I'm going to write on this piece of paper, and that is also, don't forget the delta H for the reverse of the reaction. In other words, if you flip the reaction, the delta H, you change the sign. So if we wanted to do the reaction of CO2 gas plus 2H2O liquid yields, so put this as the reactants and this is the products, CH4 gas plus 2H2O gas as products, you would have the same delta H, you would just flip the sign, it'd be positive 890. Does that make sense? Any questions so far? All right. Hess's law allows us to calculate enthalpy data for reactions which are difficult to carry out directly. So it says there's carbon solid plus oxygen gas produces a mixture of carbon monoxide and carbon dioxide. So if you get in other words, you get part of this makes carbon monoxide and part of it makes carbon dioxide. But if you were to combine those two reactions together, then you can get your overall enthalpy change for the whole thing, even though some of them are going to do this and some of them are going to do that. That's all that's really saying. Okay. All right. So hopefully the concepts that I've gone through make sense somewhat. Now it's a lot easier once you start seeing the actual kind of problems and work. So let's go to that. All right. Let's start with the page 186 sample exercise. Okay. The enthalpy of reaction for the combustion of carbon to CO2, carbon dioxide, is negative 393.5 kilojoules per mole carbon. And the enthalpy for the combustion of carbon monoxide to carbon dioxide is negative 283.0 kilojoules per mole carbon monoxide. So, see here, equation 1 is the top thing they were talking about. Carbon combustion plus O2 gas yields carbon dioxide, CO2 gas. It's a little different combustion reaction than our typical. It produces delta H of negative 393.5 kilojoules. Okay. Now, Notice this. Negative 393.5 kilojoules per mole of carbon, right? So delta H, negative 393.5 kilojoules per 1 mole of carbon. Remember, in a balanced equation, the coefficients represent the number of moles. Okay, so that's where we get into the second part, which you're going to look at and kind of probably want to strangle me because like, making it more complicated. Yes, we are. All right, so look at the second equation. Combustion of carbon monoxide into CO2. So again, carbon monoxide plus oxygen, we're just producing CO2, kind of a different type of combustion. Now, negative 283.0 kilojoules per mole of carbon monoxide. Right? Okay. Here's where the balancing part comes in, the weird part. Okay, so I'm going to do this. I'm going to do this in red because this isn't really part of solving the problem, but I want to explain to you why this is the way it is first. Okay? So, if we were to write this equation, like this, okay, and then we were to balance it. If I balance this, I get, I think I need a 2 here and a 2 here, right? Like that. That balances it. 2 carbon, 4 oxygen on each side. Okay. Now, okay. How many moles of carbon monoxide do we have in this balanced equation? Yes. Right. 2. Because of this. Right? We got 2 moles of carbon dioxide. What did they tell us our enthalpy is? Right here. Negative 283.0 kilojoules per 1 mole of carbon monoxide, right? So, if we were to look at this, and we were to say we have 2 moles carbon monoxide for every 1 mole of carbon monoxide, we have negative, oops, sorry, I'm looking at the wrong one. We have negative 283.0 kilojoules. Everybody okay so far with where I'm getting the numbers from? The 2 for the moles came from the coefficient, and then this is from this part right here that they told us, negative 283 kilojoules per 1 mole, right? So watch what happens. This is, what is it?
Negative 566.
Thank you. Negative 566 kilojoules, right? Okay, so the delta H for this reaction would be negative 566 kilojoules. Is that everybody okay with that idea so far? Is it making sense? All right, but with Hess's law and the enthalpy stuff, a lot of times they don't, because it depends on the reaction and stuff, but a lot of times they don't like to multiply up. What they usually like to do is they always like to think, when you're thinking about the enthalpy for a certain substance, they always like to think of it per mole, like the amount for 1 mole. All right, so all they did to get this, and this is why we have a coefficient that's a fraction, which is a big no-no up until now. is all they did was they said, you look at what they want it per mole of, and you get that number to 1. Or or assuming they want 1 mole of it. So per 1 mole of carbon monoxide, so if we look at carbon monoxide, how many do we have? 2. So you literally go then and you get this to a 1, which means you would divide by 2, and you do that to every coefficient. So you divide by 2, and whatever you do to the coefficients, you also do to your delta H, because it's a ratio. Okay, so now everybody see where the numbers are coming from now? Here. So it's now a 1 here. This, in front of oxygen, becomes a 1/2. And in front of your CO2, it becomes a 1, because it's 2 divided by 2. And then we divide this by 2, and it gets us to what they gave us here per mole. Okay, now, in general, if you're writing it, no, you don't have to divide this. This they already gave us per mole, so we would already known that here. We would have just had to figure out the balancing for the rest of it. Okay. Does that make sense? Okay, questions so far? All right, so like I said, that's not actually part of solving the problem, but that is hopefully to help you understand why all of a sudden it's okay to have fractions for our coefficients in the equation, right? Okay, so we are going to use these 2 equations that they gave us to calculate the delta H for this reaction, right? So here's what we're going to do. We're going to take these equations, and we need to make them end up looking like this. So this is like in algebra. Remember when you guys would do like the 2 or 3 variable equations, use like the 3 variable equations, the x, y, z, and you'd have to eliminate and substitute and stuff. You know what I'm talking about, like the x, y, z stuff. That's essentially what you're doing here, except with chemical equations. All right. So what you do is you look at your goal. I'm going to highlight this. This is our goal equation. Okay. That's what we want to end up with. So you look at your goal equation and you ask yourself, what can I do with my other 2 equations to end up with this when we're done? All right, so let's look. Now, if there's something that's in more than one, I usually ignore that. You're trying to find things that are only on, things that are something in here that's only on one side of the equation, or in only one of your starting equations if possible. So in other words, like, see how CO2 is in both of them? I don't want to use CO2 if I can help it, because then I don't know which equation I'm going to use or how much of it or whatever. But look at so if I look here, I've got carbon, right? Notice how there's no carbon in the second equation? That means that whatever carbon is down here in this goal equation has to come from that first one. Does that make sense? Okay, so the 2 things you're looking for is we need to get it on the correct side of the equation, the reactants or product side, and it needs to have the right number of moles. So if we look at our goal equation, how many moles of carbon do we have? 1. What side is it on, the left or the right? Left. It's on the left, it has 1. So let's look up here. We need to make sure that this equation is on the left and it has 1. So is carbon on the left? Yes. Does it have only 1? Yeah. So this one actually makes our life really easy. We're going to leave it exactly the same. This equation, so I'm just going to write it. And I'm going to put my delta H over here. Okay. Now, and here's the other thing, is you're only going to use each equation once. So once you've used the equation, you can like check it off, and you're not gonna use it again. Okay. All right. So let's look at our second equation. We have to find something unique to this equation that is in this in the goal equation that's unique to this one. So what about carbon monoxide? That looks good. It's not in the first equation, correct? So let's look at our goal equation. Same type of deal. Which side do we need the carbon monoxide on? On the right side. Is it on the right side? No, it's not. Okay. So that's one thing. So we have to flip. I'm just going to write here. We're going to flip the equation. Okay. Now, how many moles do we need? 1. That's what we have, correct? So the moles thing is okay. We don't have to mess with that. We are just going to flip this equation. Literally, reactants become products, products become reactants. So I'm going to put CO2 gas on the left side here. And on the right side, I'm going to put CO gas plus 1/2 O2 gas. Okay, what happens to our delta H?
Positive.
Yeah, good. You switch signs, right? So if you flip it, the sign changes. So our delta H, same amount, but positive. So 283.0 kilojoules. All right, how are you feeling so far? Okay. Now, all we're going to do is do exactly what you would do in algebra. You're going to combine, you're going to add the two, you're going to combine the two together and simplify. So I'm going to write it, I'm going to kind of write everything out so you kind of see how it works. So in other words, I'm going to write all the reactants on the left and all the products on the right. So carbon solid plus O2 gas plus CO2 gas yields CO2 gas plus CO gas plus 1/2 O2 gas. And I'm not going to do I'm not going to do my delta H yet. All right, now let's look at this. So, use a red pen for this part of it. Or maybe. Try light blue. Okay, now, just like in algebra, you're going to simplify. So anything that's basically you're going to simplify anything that's the same on both sides, including the coefficient, they cancel each other out. Or you could say you pull one to the other side and subtract it, however you want to look at it, okay? So we've got, actually that is important. Okay, so our CO2 gas is on the same on both sides, right? The same amount. So those can cancel. Okay. Now, we've got carbon solid here. We've got carbon dioxide. We've got oxygen, oxygen. Now, we've got oxygen on both sides, but they don't cancel. They don't have the same amount, correct? All right. Now, in our chemical equations, you don't want something being negative. Like, you don't want minus something, typically. So if you end up with an equation that has, like, carbon solid minus O2, like something went wrong somewhere, okay? Or at least in your final equation or whatever. On this, so, and if we look up here, what's our goal? What side is oxygen on, the left or the right? The left. So we want to get all of our oxygens to the left. So we're going to take this and we're going to subtract 1/2 oxygen, both sides. All right. What do we end up with? Well, over here, we end up with solid, carbon solid, plus 1/2 oxygen, right? Because 1 minus 1/2 is 1/2. Yields, what do we have left on the right side? Just carbon monoxide gas. Which is our goal. Okay, now, how do we get our delta H for this? We just combine these. So negative 393.5 plus 283 gives us a negative 110.5 kilojoules, which is technically our answer. Okay. Make sense? Questions so far? Okay. Let's take a look at the second one. Second one is the same thing. It's just with 3 instead of 2. 3 equations. Okay. So we've got our goal equation here. And we've got our 3 starting equations down here. Okay. Now, this is what our goal equation we want to have. So, it doesn't matter which one of these 3 you start with. Like you don't have to start with the top one always. You can do any of them. Can anybody see one of them? Like see something in one of them that's not in any of the other 2 that we could move around or manipulate? Yeah. So.
Carbon in the second.
Okay, carbon in the second one. So you look, carbon's not in either of the other 2 equations, right? So that's a good one to pick because we need it in our goal equation, and it's not in there. So what do we need to do to get it to be the same as what our goal equation is? Double it. So we're going to double times 2 everything in this equation, coefficients and our delta H. So this becomes 2 CS plus 2 O2 gas yields 2 CO2 gas. And then our delta H, we double that as well, right? So that becomes negative 787 kilojoules. Okay, everybody okay so far? Like, makes sense? Okay. So we've used the middle one. Anybody see the other 2? What we would, any substances? Jacob? Okay. Which substance are you looking at on that one? Good. The C2H2, right? That's only in the top one. It's not in any of the others. Okay, and then like you said, if you look, the C2H2, we only need 1, which is what we have, but we've got to flip it. It's got to be on the right side. So we are going to flip this, right? So we get 2 CO2 gas plus H2O liquid. And so on the right side now, we're going to have the C2H2 gas plus 5 halves O2 gas. Right? What does that do to our delta H? Good, change the sign. So our delta H, same amount now because we didn't do anything to the rest of it, but we're going to change the sign. So it's going to be 1299.6 kilojoules. Right on the edge. right? So, all right, so we've used the first one and the second one. Now, what about the third one? Okay, so do we need to do anything to the third one? No. The hydrogen gas, right? It's not in any of the other two. We just need one of them. So this one we're just going to leave the exact same way it is. So H2 gas plus 1/2 O2 gas yields H2O liquid. And our delta H stays the same, 285.8 kilojoules. All right, now we combine them. Okay, we get, let's see. So 2 carbon solid. Now I'm going to combine like I've got my O2s here. I've got 2 O2 and I've got 1/2 O2. So I'm going to combine those. I'm going to make it an improper fraction. So 2 O2s is 4 over 2 plus 1 over 2 is 5 over 2 O2. So I combine those two. Plus 2 CO2 gas plus, I don't know if I'm going to have enough room for this, H2O liquid plus H2 gas yields, I'm going to write down here because I'm going to run out of room. 2 CO2 gas plus C2H2 gas plus 5/2 O2 gas plus H2O liquid. Okay, now I'm going to cancel anything is the same on both sides, or I'll combine. So my 5/2 O2 on both sides cancel each other. My H2O liquid. Now, remember, when you're looking at canceling and stuff like that, they have to be exactly the same, including the states of matter. Okay? And my 2 CO2s also will cancel out. So what am I left with? 2 carbon solid plus H2 gas yields C2 H2 gas. That's it, which is our goal equation, right? And now to get the total, we just add together all of our delta H's here that we figured out, and we get a delta H of 226.8 kilojoules, which is our answer. All right, how do we feel? Decent? Okay, now, I showed you guys all of that to show you how it works. Now, let me show you. I want you to understand what's happening with the equation and being able to see that, right? All right, now, watch this fun stuff. Change pen color here. I don't know if you'll be able to see it when I upload it, but okay. So you've got a problem, and as long as all it wants is the delta H for the reaction, if that's all it wants, all you have to really do is figure out what you have to do to the step equations. Do it to the delta H and add them all together. Okay, let me show you what I mean. If all they want is the delta H for a combined reaction, so all we would have to do is figure this out. Now, you've got to be, like I showed you all this, you've got to be pretty confident that you're doing the right stuff in here. that like you're doing the right stuff over here. But if we determine that all we have to do to these is flip our first one, multiply our second one times 2, and leave our last one the same, right? So if we figure that out, we actually don't have to do all of this, like adding it all together and then canceling out, as long as you're careful and you know that you did the right things to the equation. Okay? Then all you have to do, once you've determined you flip times 2 like this, is you just do that to each one. So the top one, my delta H. So delta H for the first one is going to be flipped. So I take -1 times plus, what happens to the second one? Multiply by 2, right? 2 times -393.5 plus, nothing happens to the third one, right? -285.8. And we get the stuff over here with the equations and the canceling is just confirming that you're ending up at the goal equation. This is just almost like a check. All that does is confirm that you did the right stuff to the equations to get to the goal equation. But we already know the goal equation. So in reality, all we have to focus on really are the delta H's and then what you need to do to each of the step equations to get to the correct goal equation. Okay, now, if you want to do the equations out like this, and you want to cancel stuff just to make sure, or at least at first, if you want to just kind of make sure you're getting stuff in the right idea, go ahead, that's fine. Okay? But if you know what you're doing, now just be careful. Okay, because without doing the balancing of the equation part to sort of back you up, then you won't necessarily know if you do something wrong to your delta H's. Okay? But in reality, you can just focus on the delta H part and what's happening to each thing. Does that make sense? Any questions? Okay. The homework is the worksheet. You're essentially kind of doing the same thing. Now, when you do this, if you are not writing them all out like this, I need to at least see what you did to each delta H. So like I want, if you're not writing it all out, I need to see this stuff like I wrote in green here. And I need to see this like this. So like you could do it off to the side over here by the delta H. You could like flip and whatever you want to do, that's fine. But I need to see that part of it, okay? And if you get stuck, if you can't get it, then do this. Do the actual equations out and figure it out, okay? Another helpful hint, don't forget you can multiply by a fraction as well. So like say something has a coefficient of like 3x and you only need 2 of them. If you multiply by 2/3, that gets you a 2 in front of that variable. Okay? All right. Let me